So my name's Marc Joie. I have the pleasure to chair this session. So this is the first one on practical cryptography. There will be 3 talks in this session, and the first one is on sum preserving encryption, and talk will be given by Sarah. I see online, Sarah, can you hear us?
Yes, I can.
Perfect, so you can start whenever you want.
All right, well, thank you. So welcome everyone. So I'm going to talk about new algorithms and analysis for sum preserving encryption. And this is joint work with Scott Yellick. So I'm going to start by introducing the problem of sum preserving encryption. So the idea is we're going to create an encryption scheme where the ciphertext and plaintext are both going to be integer vectors, and they're going to have the same sum. So if we sum up all the points in the vector for the plaintext and the ciphertext, they're both going to have the same sum. In addition, each of the components of the vector are typically going to be bounded between 0 and some maximum of d. And this problem was introduced by Tajik et al. In 2019, and they looked at a particular application of sum preserving encryption, specifically thumbnail preserving encryption. So the idea is you want to create an encryption scheme where the thumbnail of the original image and the encrypted image are the same. So we're create the thumbnail by dividing an image into B by B blocks of pixels. And then we're going to replace each block by the mean pixel values, the average of all the pixel values within the block, to create a smaller image. So if we take each of these same blocks and we apply sum preserving encryption to the blocks, then the sum of the pixels in the original image and the encrypted image will be the same. Thus, the mean will be the same, and we've preserved the thumbnail between the original image and the encrypted image. All right, so I'm going to give a little background on this problem and then discuss our new algorithms. So you can think of sum preserving encryption as it's a special type of format preserving encryption. And there's been a lot of work on format preserving encryption. It was originally studied by Brightwell and Smith in '97. It was formally defined and analyzed by Belair, Ristenpart, Rogaway, and Stigers in '09. And they used a rank and cipher unrank construction, which I'll talk about further examples of that here today. And again, it's widely studied and even standardized. So Tajik et al. Introduced this idea of sum preserving encryption, as I said before, and they focused on the problem of creating a thumbnail encryption scheme. Okay, so I mentioned that this idea of rank and cipher unrank is going to be important, so let me just review that real quickly in case you haven't seen it. So the idea is we're going to start with a plain text, then we're going to apply a rank algorithm. So we're going to rank each possible plain text between 0 and n-1, where n is going to be the total number of possible plain texts. So we first start by ranking it, then we have an integer, and we can apply a standard cipher to get another integer, right? This is our encrypted integer, and then we apply an unrank algorithm to get back to a ciphertext. And this is a standard technique in format preserving encryption. So Tajik et al. Realized that we could use this approach for the problem of sum preserving encryption. And so they proposed this idea of representing a string, representing a vector as a string of ones and zeros. So this is the stars and bars construction from combinatorics, if you've seen that before. So we're basically going to, let's say, look at our example, the first number is 5, we're going to replace that with 5 ones and then a 0. So the zeros are going to serve as our separators. So we'll have 1 less 0 than there are points in our vector. And then our second number is 3, we would have 3 ones followed by our separator and then our final one. So if we represent our vectors of integers as binary strings in this fashion, then this is a regular language, and there's some known techniques we can use to turn this into an encryption scheme. However, this has high time complexity, and it's relatively impractical in this situation. However, Tajik et al. realize that if we do this with just vectors that have 2 points, so if we just have length 2, then this is pretty straightforward. And if you've got some downtime during the next break between talks, you could work out how we could rank vectors of length 2 with a fixed sum. And so they use this idea to create a sum-preserving encryption scheme. And it actually can be thought of as a Markov chain. And so I'm going to talk a little bit more about it from the Markov chain perspective in a little bit. So I'm going to present their algorithm, not exactly how they presented it, but as a Markov chain, which they did realize, point out that this is a Markov chain. So the idea is they're going to repeat this algorithm in multiple rounds. So they're going to start, again, you're starting from a vector of integers, and they're going to randomly shuffle those points. All right, so you randomly shuffle the points, and then we're going to pair adjacent points to get a perfect matching. All right, randomly shuffle, pair adjacent points to get a perfect matching. And then now within our matching, we have pairs of points, and I just mentioned that we could rank and Cipher unrank these points. And so we're going to replace, using this rank and Cipher unrank approach, we're going to replace each pair of integers uniformly at random from all the possible valid choices, right? So we have to preserve the sum, and we have to preserve that component bound. All right, so for each pair in our matching, we're going to replace uniformly at random from the possible choices. And then we get another vector that's going to have the same sum and respect those component bounds. All right, so today, our results, we give the first proof bounding the mixing time of the Tajik et al. Algorithm. So, the natural question you might ask when presented with an algorithm like this is how many rounds is sufficient, right? How many times do we have to repeat this? So we give the first formal bound on the mixing time. And in addition, we give 2 practical rank and unrank algorithms that we can use for sum preserving encryption. And we also create prototype implementations with performance comparisons comparing these 3 different algorithms. All right, so in the rest of my talk today, I'm going to go over briefly our mixing time bound and some of the proof techniques behind it. And then I'll present the 2 rank, I'll describe at a high level the rank and unrank algorithms, and then show you briefly the performance comparisons. Okay, so we're going to ask this question for the mixing time bound of how many times do we need to repeat this algorithm? And Tajik et al. Gave a heuristic algorithms for what secure round choices would be, but no formal proof. And so that's what I'm going to present today. And they tested performance with 1,000, 3,000, and 5,000 rounds. Just to formalize, I'm going to talk about the mixing time. And here the mixing time is going to be the amount of time until the difference between the distribution at time t and the stationary distribution is less than epsilon. All right, so we're going to parameterize this by epsilon. All right, and we show that if n is the vector length, d is the component bound, and s is the fixed sum, then the mixing time is upper bounded by n log of the minimum of dn, 2s, and 1 over epsilon. All right, so how do we do this? Well, we're going to use a path coupling technique due to Dyer and Greenhill in '98, and this is a standard technique in the Markov chain community. So before I'm going to kind of give you a high level view of what the proof looks like. And before I jump into that, though, let me just kind of tell you a little bit about the techniques that we use. I'm sure not everyone's familiar with them. So we use path coupling, which kind of followed on to coupling. So the idea of coupling is we're going to simulate 2 processes, X and Y, and each of them, if we view it in isolation, it looks just like that Markov chain. And so we're going to simulate these processes until they agree. And once they agree, they stay together. And it turns out if we can bound how long it takes before these processes agree, this is called the coupling time. And this will give us a bound on the mixing time. So we can use the coupling time to bound the mixing time. And how we do this is we generally show that at each step of the Markov chain, the distance between the 2 chains is getting closer in expectation. So the expected distance between the 2 chains X and Y is decreasing. And here we're going to use the Manhattan distance. Okay, All right, so in coupling, again, we want to show that the expected change over one step from any arbitrary pair of configurations. So we have to show that this happens for any two configurations in our state space, any two possible, vectors. Path coupling makes this process a lot easier because we can just look at a restricted set of pairs of configurations. All right, so we don't have to look at all pairs, we can just look at a subset. And in this particular case, we're going to choose to only look at pairs that differ on exactly 2 points. So every single other pair in the vector is this every single, X and Y match on every single other point except for just 2. And so we only have to look at these special vectors that only differ on these 2 points. And just to kind of give you an idea why this works, if we show that you can find between any arbitrary pairs of configurations, you can find pairs that are in this special set, right, that only differ on 2 points. And so the expected change in distance between any two arbitrary configurations is bounded by the sum of the expected changes between those special pairs. And so we can use those to get a bound, to get our bound overall. Okay, so just to give you an idea how this works, so again, we're using the Manhattan distance, and we're looking at vectors that just differ on 2 points. So, right, so here there's, again, X and Y agree on everything else except for these 2 special points. And we want to show that after a single step of the Markov chain, the expected change in distance is going to, right, the distance is going to decrease. All right, so just to remember our Markov chain, right, it starts by randomly shuffling the points, and then it pairs adjacent points. So if after our random shuffling, if these 2 points that differ, if these happen to be adjacent, right, then our distance decreases to 0, right? That we can choose the same new pairs of points in each of our chain X and Y, and the distance decreases to 0. So this is the good case, right? This is going to solve everything. The downside, though, is that if these pairs of points, right, if these match with other points, then it's much trickier. And one of the things that makes this really tricky is that now if we look at the 2 chains X and Y, the sums are going to be different. And so that means that in many cases, the number of possible, right, remember we're choosing uniformly at random from all the possible ways to replace these points. And so they're going to have a different number of choices, which means that we're going to move to the different choices with different probabilities in the 2 chains. It turns out we can still show that the expected change in distance, that we can come up with a coupling, right? So we come up with a coupling and we show that the distance will always stay the same or decrease. But it's quite tricky and there's a lot of details that I'm hiding. So I'm not going to go into those details, but that's what makes it interesting, I guess, or tricky is that part. All right. Okay, so I told you we had kind of 2 types of results. One was this mixing time bound, and the other one was the rank and cipher unrank. Okay, so we have 2 algorithms for ranking and unranking, and I'm going to talk about the first one just a little more quickly because it's not quite as interesting. So the first algorithm for ranking is going to rank the vectors directly using lexicographical order. And here we're going to build on algorithms for unranking that were developed by Stein for use in random sampling. So he's trying to do something different. And he gave an algorithm for unranking according to lexicographical order. And we came up with, added on to that one for ranking. This algorithm is going to rely heavily on a table, which we can pre-compute, and that's going to store, so every point in the table NS is going to store the number of vectors of length n with some s, and the table, all entries across the table will have the same component bound. And with this pre-computed information, we can rank according to lexicographical order, and if you're interested in the details, you can take a look at the paper. The other ranking algorithm is based on what's called, we call recursive block order. And as far as we know, this is not an ordering that has been used before. And so to describe this order, so if you want to order 2 vectors according to recursive block order, you're going to divide the vector in half, and you're going to look at the left sum and the right sum. And if the left sum is smaller, it's going to be smaller in the order. If the left sum is greater, it's going to be later in the order. And if they're equal, and this is where the recursive part comes in, if the left sums are equal, well, then we're going to take a look, and how the vectors relate depends recursively on how the left half relates to the right half according to recursive block order. All right, and so here's an example. So this is different than lexicographical order. Again, we're going to split the vector in half and we're comparing the left sums to see where it falls. And if they're equal, then we repeat. All right, if we want to rank according to recursive block order, and I'm going to go through this a little bit quickly, so if we want to come up with a ranking based on this ordering, we need to determine if we have a particular configuration, we need to determine how many configurations are smaller in the order. Right. And so there's basically 3 different ways that a configuration can be smaller in the order. And so we need to count how many there are in order to rank. And so we can do this using a combination of recursion and the table values that are stored. So if we look at this first, the piece in yellow, right, the number that have a smaller left sum, well, we can count this up using table values. The second one, if they have an equal left sum, but XL is less than YL, right? Then we need to determine the rank of XL. And then for each of those, right, for everything that's smaller in rank, the number of configurations there are, right, we multiply the number of ways there are to fill in the right half. And then to get that final piece in green, we're going to take the rank of the right-hand side. And if we add these 3 things up, we get the rank of a configuration. And you can take that recurrence and turn it into an, it's pretty straightforward to go from there to an algorithm. The nice thing about recursive block order is if you see here, we're only looking at when we make recursive calls, we're dividing in half each time. So we actually only need to see we only need to compute 2 log n rows of that table versus lexicographical order. So we need much fewer rows, which is going to give us some performance improvements. So both of these algorithms rely on this C table. And so I'm just going to describe quickly, we come up with 2 different ways to fill this table. And the first one is similar to what Stein does, but in fact, so he doesn't frame it as dynamic programming, which is what I'm doing here, but it essentially is the same technique for filling the table. We actually use a cumulative sum instead of storing the C values directly because it leads to some improvements in the algorithm. And so you can come up with a recurrence for this table. The idea here is we're going to look at the very first vector, the very first point in our vector. And so if it starts with 0, we can count those recursively as shown on the slide. And if it starts with some number that's greater than 0, right? So if it starts with something that's greater than 0, then we can just look at the number of configurations within points and sum 1 less. And then we take each of those and we add 1, and that gives us something, right? That gives us something in the original C of NS. However, in some cases, we're going to be over counting here because adding 1 to the first point in the vector might take us above our component bound. And so that's where this third term comes in. I mentioned that in the last, right, in our second ranking algorithm, we only need to look at log n rows of the table, or 2 log n at most, log n if it's a power of 2. But the dynamic programming version of filling the table, actually, you would need to fill out all rows, right? And so you wouldn't get that improvement. So we also can fill the table using generating functions as well, and that allows us to only fill the rows that we need, and we can take advantage of the fact that we only need those log n rows of the table. Right. So in addition to the mixing time bound and the ranking algorithms, we did prototype implementations and compared the running time of these 3 different algorithms. I'm not going to go over the slide, the numbers are up there. I will say that for the specific example of thumbnail preserving encryption, it seems like the ranking algorithms are going to get us an improvement. But again, which algorithm is better is going to depend on your particular choices of N, D, and S. And as we get to larger values of N, the ranking solutions struggle because we have to pre-compute this table, and that table starts to get really large. All right, so in summary, I showed you well, I guess I hand waved a lot, a proof of the bounding the mixing time of the Chijik et al. Algorithm. And I showed you, or we gave two practical rank and unranked algorithms for sum preserving encryption, one based on lexicographical order and the other based on this new recursive block order. And we created prototype implementations with performance comparisons. That's it. Thank you.
Thank you, Sarah. So do we have questions for the speaker? Okay, maybe online, I don't know. No? So maybe, I saw salary as one of the application. What is preserved in that case? I saw I saw in one of your slides that salaries was one of the application. So what do you preserve in that case? So the sum of the salaries?
Oh, yeah, we're preserving the sum. Mm-hmm. Yeah, so all of our work preserves the sum. I think you could definitely possibly generalize some of these methods if there was a different parameter that you wanted to preserve, but we only looked at sum preserving. A lot of the ranking algorithms are very specific to the sum.
And assume that someone new joined a company, and so in that case, so the sum will change, but then you can deduce the salary of that person. Is that correct? So assume that someone new joined a company.
Oh, yeah, the sum would change. You would have to, re-encrypt.
Okay. And just the last question. So is there a plan to make a product of what you presented?
Not as far as I know. I would love it if there was, but.
Okay. So thank you.
Yeah, thank you.
Okay, so we can move to the next talk. Thank you, Sarah. So next talk will be on the Elizabeth string cipher, and the talk will be given by Aurel.
So hi everyone, thank you for the invitation. So this talk is going to be about hybrid homomorphic encryption, which from now on I will call HHE, which is a tool used in a fully homomorphic encryption to solve the problem caused by the expansion ratio. When you're doing FHE, you have to deal with a huge expansion ratio. So this is an illustration of it. So if you want to send some data on the network, and you have a small plain text, the corresponding ciphertext is going to be huge. We are going to try to use what comes with FHE to reduce this. So on the screen, you have a usual setup of FHE, where someone is trying to send some data to a server to do some computation, but doesn't want to reveal them. And the server is going to compute homomorphically on them. But once again, sending this data requires a lot of bandwidth. So what we would like to do instead is use another crypto system, much lighter, with a small expansion ratio. And then, since the server can compute whatever he wants, it can also decrypt this small ciphertext to obtain the fully homomorphic encryption he would have had without that, and then compute whatever he wants. But to do so, it needs to have the secret key of the new scheme. So we also have to do one sending in fully homomorphic encryption at the setup, which contains a secret key. So several HHE schemes have appeared over the year, and they are trying to optimize different criteria. The main three being the economy in terms of boundaries in itself, and the other two being the latency and the throughput. And nobody really agrees on which one is the best. So the latency is the time you have to wait to go from a small symmetric scheme, so my gray box here, to a red one on the server, an operation that is called transciphering. And the throughput is the amortized time of the latency, so it's the time that it takes to transcipher only one bit And it makes sense when you use packing in FHE, which is the ability to store several messages in a single ciphertext. So we wanted to, I'm here to introduce a new scheme called Elizabeth, which will be here on the scheme. But the main idea that we want to introduce is that it doesn't really make sense to compare all these schemes in terms of latency or throughput as standalone use case, standalone scheme, sorry. So in the current state of the art, schemes are designed to optimize some aspect of the HHE, so some aspect of the transciphering time. And then the comparison are done as if the scheme were standalone. And we don't think it makes sense in FHE since it's losing sight of the fact that in FHE we want to compute something with output of the HHE scheme. So what we did instead was to start by thinking in terms of use case, what we want to do once we have transciphered, and then design a scheme that will be optimal for that kind of use case. So to evaluate an HHE scheme with a use case, we need a use case. And we choose one that is very common in FHE, and it's machine learning. So it comes with its own set of constraints. First off, in machine learning, we want to use as many bits as possible because neural networks usually work with 32 or 64 bits input. And then we want to be able to compute fast because when you do machine learning, you don't want to wait a long time to have an answer on what you're trying to compute. And then FHE comes with its own set of constraints. So we choose to use TFHE, that is a state-of-the-art crypto system fully homomorphic. And in TFHE, you don't have the ability to pack messages. So that was something that we knew we would have to deal with. And TFHE is useful when you want to do modular additions and evaluation of megacyclic lookup tables. That is lookup tables in which the second half of the values are the opposite of the first half. Another missing item on my slide is that in TFHE, you cannot store very large messages in a single ciphertext. So we knew that we would have to work with a few bits. So the trade-off was to use 4-bit messages. That was the best we could do to have a small crypto system, a fast crypto system to evaluate while storing as many bits as possible in a TFHE ciphertext. And for the fast evaluation, we made it so that our crypto system will be easy to evaluate on multiple threads at the same time. And regarding the constraints caused by TFHE, we just chose to call them a toolbox instead of constraints, and we use them to design the scheme. So now let's dive into how our scheme is done. So it's called Elizabeth, and it's thought as a successor for a crypto system called Philip, which as all state-of-the-art HHE scheme is based on the filter permutator paradigm introduced by Philip. So the idea is that when you want to generate a key stream, you start from an internal state, and then you do some computation over it. But when you do so in FHE, you add some noise in the output. And if you do it too much, at some point, your key stream will be so noisy that you won't be able to use it anymore. With the filter permutator paradigm, you start from an internal state, and you apply a key stream generator function. And you will always use the same function on the same internal state. So the bit that you produce will always contain a fixed amount of noise. So how are we going to do that? By adapting the filter permutator paradigm to the group filter permutator as a group filter permutator paradigm. So we start from a key register, and using a public PRNG, we are going to choose a subset in it and shuffle it, and then add some random noise in it. So all of these operations are noiseless because choosing a subset and shuffling it, it's not FHE, it's just moving blocks around. On the whitening, it's adding a clear text to a ciphertext, and it's noiseless. So at this point, nothing is noisy in what we did. And then we are going to apply a filter function. And only in the filter function will we add noise to our ciphertext. So in the end, Elizabeth is entirely defined by its filter. So here it is. I do realize there's a lot of slides, so we're going to break it up. The first thing you have to notice is that there's only 3 different things on this. You have 5 input x1 to x5, modular additions, and 8 boxes S1 to S8 that are negatively cryptable and that are computed through a bootstrap homomorphically. These lookup tables are the costly part of the operation. Luckily, the first 4 can be computed separately because you don't need the output of each one to compute the others. So you can do that in a 4 separate thread. Then you have an addition, so you have to wait and synchronize. But the next 4 can also be done separately in 4 different threads. So in the end, to compute this box, you only have to pay for 2 bootstraps, and you can compute 8 of them. And this is just a part of the full filter, and the actual filter is this operation done 12 times in parallel. So the entire filter of Elizabeth consists in 96 bootstraps, but you only pay for 2 of them thanks to multi-thread. So now let's have a look at our use case. So this is a neural network that we used for the use case, which is rather small, I think. I was told so by people that do understand what machine learning is. And what it does is classifying pictures of clauses. And believe it or not, but this picture is actually too high def to be used in FHE because it uses 8 bits of gray, and we can only use 3. So why 3 and not 4? Even so, Elizabeth can store 4 bits messages. It's because to enable fast computation with TFHE, you need to set the most significant bit to 0. So we can only write in the 3 next bits. So by doing so, the neural network loses a bit of accuracy. So it can only answer correctly 90% of the time. But it's okay for us because we know that with FHE, we are going to lose a bit of accuracy. So now regarding the timing of Elizabeth, it has been designed to be to use less constraining parameters than any use case that it could be used for. So actually in this table, I'm only interested in these 3 values. So if you use Elizabeth with optimal parameters, it's going to be sufficiently efficient. So the timing doesn't mean much because it depends on what computer and hardware you're going to use. But what you can see is that if you use Elizabeth with a use case, then the timing are multiplied by a factor 5, and it comes from the fact that the parameters of the use case, are going to be much bigger than the parameters of Elizabeth. And for every different set of parameters that you want to use in FHE, you have to send another key to the server. So you could choose to use Elizabeth as a plug-and-play crypto system and send nothing to the server, and then the timing are going to be a bit big. But you could also choose to send its own set of parameters for Elizabeth and gain some time. So if you just do an inference, that is an evaluation of the neural network in FHE without HHE, it's going to take 5 seconds. And if you use Elizabeth with the parameters of the neural network, it's going to be much larger. But once again, it can be much reduced if you use parameters for Elizabeth that are different than the one from the neural network. And in terms of efficiency bandwidth-wise, Elizabeth will reduce the bandwidth used since the very first inference. And if you choose to use the 2 sets of parameters, it's going to take a bit more inferences, so around 2,000 inferences, but it only takes 40 hours, so it's not much in FHE time. So from there, what do we want to go? Well, first off, we would like to be able to transcipher much bigger message at the same time, because with 4 bits, we have seen that there's not much that we can do. We also think that we should look at that from the machine learning point of view. So without even using cryptography, how can we do better neural networks that are easier to evaluate with FHE? And lastly, we should look for more relevant use case because once again, we think it doesn't make sense to consider HHE without a use case, but we also think that we need to find use cases that are relevant to HHE. So we chose to use this use case because FMNIST is a very common data set in machine learning, but maybe it's not what you want to do when you use HHE. And we think that people that do understand what is machine learning should look into HHE and find a relevant challenge that will help compare feature schemes. Thank you very much for your attention. And if you have any question, I'd be happy to answer.
It doesn't drop out. Okay. The questions, remarks? Online, do you have questions? So you told us that Elizabeth was the successor of Philip.
Yes.
What's the main difference between the two ciphers?
Philip worked in 1-bit messages, and with Elizabeth, we are able to encrypt 4 bits at a time. So that's the main difference between Philip and Elizabeth, and actually between Elizabeth and most HHE schemes, is the ability to work on 4-bit messages rather than in just 1-bit messages. And there are some other HHE schemes that work with several bit messages, but then the output are in infinite fields rather than in Z16. So it's less easier to do any computation on them afterward.
Okay, thank you. Okay, so if there are no more questions, let's thank the speaker.
Thank you very much.
So next talk is on related key boomerang attacks on AES.
And here's the link. Hello. So, hello everyone. Let's get started. So, as you can see here, this table summarizes existing attack against AES 1 and 92. And note that here, by click is not really an attack. It just improves the exhaustive search with a complete loop on the key space. And the current bedtime complexity for an attack on route is 2 to 176 for a related key boomerang of Pirokov and Kovatovic. And in this work, we found a new related key boomerang attack. Its time complexity is 2 to 52 times lower than the best-known attack. So here is the boomerang attack. In the left is the best-known attack of Pirokov and Kovatovic, and in the right is our attack. Green by here is that means the known different, and we have our attack has the probability is 2 to minus 108 instead of 2 to minus 110. It's a bit better, but it's almost the same probability. Here is a zoom on both input of both attack. So in our attack, we have more green by than the best known attack. This means we know much more information than the attack of Pirokov and Kovatovic. And in the rest of this talk, I will explain in detail how we found the attack. So anyone here knows the boomerang attack before? Raise your hand. Okay. In 1999, David Wagner was first introduced the boomerang attack, and what is studied here if the difference will be come back or not. So I will explain in a basic form of Boomerang distinguisher have an attacker as the access for both encryption and decryption cipher. So first, the attacker picks the P1 at random and asks for the ciphertext C1. And secondly, he composes P2 by adding a different alpha and gets the ciphertext C2. And after that, he composes C3 and C4 by adding the different delta to C1 and C2. And next, he obtains the corresponding plaintext P3 and P4. And finally, he checks if P3 and P4 differ by the same different alpha or not. And if alpha come back more often than a random permutation, we will have a distinguisher. And for the original approach, the cipher E divided into two parts, E0 and E1, and we need the good differential for each part. And for the input different alpha lead to the output different beta with high probability P and over E0, and the gamma lead to delta with the high probability Q over E1. And we need then the expected probability is P square Q square, with the assumption that two shells are independent. But in practice, this assumption does not always correct. And in 2011, movie shows that the boomerang never come back. And the problem comes from the extension of two shells that may exist. So to handle the dependency, then I propose the sandwich attack. Now the cipher divided into three parts instead of two parts, E0 and E1 still here, but we have a new middle pass, EM, and the EM with high probability R, and now the expected probability is P square, Q square, and R. And so how we can compute the property R of EM? In Eurocrypt 2018, CIFAR proposed the boomerang connectivity table that reduce the problem of computing the property of the boomerang switch to the one of computing it over XS block. And the BCTNG table here is the number of solutions that the boomerang come back. After that, at FSE 2019, Song and revisit the BCT and propose the BCT framework. This computes the property of boomerang distinguisher with considering the dependency. And to search for the boomerang attack, we typically use some automatic tool for search for the boomerang distinguisher. And CIFAR use MILP model to study the ladder switch to attack the Delphi. Liu and Sasaki use MILP model to direct research for the boomerang distinguisher on it. But this was only reject EM, just only one round. And recently, Delon and introduced a set of tables to calculate the probability. And they use MILP, CP, and ad hoc approach to search for the boomerang distinguisher on Skinny. And our work is based on this work. So this figure has to understand the notation used in the definition. To search for the boomerang characteristic, to search for the boomerang distinguisher, we need to be able to compose the property of the boomerang characteristic. To do that, BCT is not enough. So we need to merge the differential table. We need extra three tables here. We have the UBCT for the upper BCT, LBCT for the lower BCT, and EBCT for extended BCT. And so when given a boomerang characteristic, how to compose the probability that boomerang return? Just multiply the property of transition for each block. But how we can compute the property of transition for one particular block? that use a differential table. So here we give an example of boomerang characteristic on 3 rounds, and we need to compose the probability of this boomerang characteristic that the boomerang return. What we need to do here is just look at where we have the boomerang upper shell and the boomerang lower shell with the input difference and the output difference, and we look at where they are in the input or the output, in the upper or the lower shell, and which difference are set to 0 or 3 or specific value. And after that, we look at the summarized table here to see which property they correspond to. On this sample, in this particular block, and here for the upper shell, we have the input and the output difference are set to specific value, and for the lower shell, the input difference and the output difference set to 0, and it corresponds to DDC. That means the probability of the transition D2. On another particular block here, the input and the output of the shell are set to specific value, and for the input of the lower shell are set to 3, and the output of the lower shell are set to specific value, and it corresponds to the UBCT case. So we can compute the probability of UBCT for this transition. And that's all. So Cipher has to design a new MILP model to search for the truncated boomerang characteristics. Actually, it's similar with search for the truncated characteristic. Just copy try one for the upper and one for the lower, and adding some new variable for the known variable variable, and add some new constraint to new variable for the control of 3 variable, and there are some specific constraint for the related table to know which table are used in the computation of the probability. Objective is the search for difference to characteristics that counting number of active blocks, and instead of that, instead of counting how many different tables are used, how many tables are involved, how many tables are involved, so on, and just by the maximum probability exponential. One important property of this model is that no middle route is defined for this model. So that means this model is very generic. So we want to use this model to apply AES, to apply the AES. But first, why AES? AES is one of the most interesting algorithms in the world. So a Blockstyle has the 128 bit. F can be used a magic of 4 times 4 by. Each round of AES has the 4 operators. The round key, subby, Cipher, and column, except the last round. There are 3 versions of the AES: AES 128, AES 192, and AES 256. And our model is general, but we use AES 192 as an example because we got a good result for this version. So here is AES 192 schedule. The key schedule expands the master key into a plus round key, and problem here is that the key schedule is nonlinear, and you cannot control the difference on the key. That change a lot of things, and we need a new model. So what we have in the new model to handle the nonlinear key schedule, we use relative key conditional on the boomerang, and note that here a small change on the distinguisher may lead to a better attack. So we want to directly search for the attack, not only for the distinguisher. And actually, we cannot control the difference on the key, because if we force the difference for both input and output of an F block, then we will reject the possible value, and we look at the with key attack, and we don't want that. We don't want a key attack. So we need a key generated by a boomerang with property 1, and for our attack, we use a related key with the different SOs. In this figure, for the upper shell are above the lower shell. So for the new model, we have we define some new variable to know which different are in the distinguisher or the key recover phase. For the by the D variable, if the variable belongs to the distinguisher, the test variable if the difference is 0, and K variable if the difference is known, and S if the difference is set to a specific value. And we add some specific rule for both D and S, and there are some problems for the known variable in the key schedule, because like when we search for the differential characteristic on the AES, many of them are impossible because it does not satisfy the linear relation in the other system of equation described AES. So actually, one there's such a function in our model, but it's too much for this time. So what we need to do here is that use one type of the Ruby for each time when we found a solution, and we check if the solution is satisfies the constraint or not. So we're adding some lazy constraint to our model. That's all. So here is the if D equal 1 that means D in the distinguisher and it will propagate like that. And for D 0, that means it's not in the distinguisher, it will propagate like that. So actually in our model it's more complicated than that. And so how to compose the probability? The probability depends on the trail variable for the upper and the lower trail for input and output different. This is the Z, K, and S variable. And in practice, we found the 59 possible K, and we need to compose the social probability for each K, and we found 11 possible probability. And we were able to include the value, the probability to our model by adding 5 binary variable and 33 inequality for each aspect. And we also add extra constraint to ensure that the probability of the distinguisher is greater than 2 to minus 127. And that's all. And for the objective function, we want to optimize the complexity of the attack, but it's quite hard to compute. So we can use an approximation. So what's the master to the complexity here? In our opinion, it's the vector space of the plain text and the property of the distinguisher. So we will maximize this function for the objective function. Actually, our model is very slow and it's impossible to search for the better path. So we need to recheck the search space by recheck the number of accurate blocks per round. So for AES 256, we check the attack, but for AES 192, we found a better attack, and its time complexity is 2 times lower than the bad known attack of Recursive and Cryptography. And here is our attack. So we use the same lower trail with the bad known attack, but for the upper trail, it's a bit different for the position of active S-block. And that's the reason why a small change in the distinguisher may lead to a better attack. So finally, I will summarize our work. We propose a new MILP model to search the boomerang attack to deal with nonlinear key schedule, and we found a new way to attack again full AS 192. Its time complexity is 2 to 52 times lower than the Batman attack of Encryption and Cryptography. And we also recover the attack on AES 256. And you can read more detail on our paper on AES. F3. So for the attention, so do you have any question?
Questions? Okay, so then, oh,
Can I ask, is it possible to apply your technique to AS128 or other AS-based cipher?
Thanks for the question. So actually, our model is involved, but for AS 198, so it's our model is very slow, and we don't know how to restrict the search space to find the AS 128, so including it cannot find it. But we are in progress to improve this model because it's very simple.
okay, so let's thank the speaker and all the speakers of this session.
You can say. Why do we define that? And do I can put my hand? Of course, so how do I? Okay, hello. It's time to start. Welcome to the session. This is a session for Zero Knowledge 1, and we have 3 talks here. I'm Masayuki Abe, chairing this session. Okay, we start with short-lived zero knowledge proofs and signatures by Aras Arun. Thank you for the introduction. So this is joint work. This is joint work with Joseph Bono and Jeremy Clark. So imagine you sign something on a piece of paper with disappearing ink. Whatever you signed would vanish after some time, right? You could write a proof on paper with disappearing ink and show it to someone, and it could vanish before they show it to someone else. So the goal of our work is to emulate this